Okay, today we're going to look at some trends that occur on the periodic table, and we're going to be adding some arrows to our multi-colored periodic table. So the first one, we looked at this, and many students noted, first of all, we have an axis here called first ionization energy, and we needed to tackle what that meant. First ionization energy refers to an element being able to form an ion. So we say it's the ability to form an ion. And specifically, we're going to say it's the removal of electrons. So this is removing electrons. It means we have more positive charge there. We're producing cations. So positive charge ones. The opposite of that, again, is an anion. And anions are negative charge. So, going back to the chart, many of the students noticed that we had helium, neon, argon, krypton, xenon, and radon. If you go back to your periodic table, here they are. Okay, now let's take another look at this. Another thing that many students pointed out was that, oh look, here's lithium, sodium, potassium, rubidium, cesium, and francium. They had the lowest amount of energy needed to remove an electron. Great, we're looking at this in a very logical fashion. So then we also noticed that we had another group that appeared: aluminum, gallium, indium, and thallium. Here they are. Boron they didn't mark, but boron's also there too. If you had to put boron in here, boron would be this little bump right there. That's boron. And then the students notice one last little thing. Look, there's zinc, cadmium, and mercury. And we're going to come back to this in a second. So the first thing we're going to note on this is that we have a threshold that occurs. And when we're talking about a threshold, we're talking about your top to your bottom. And if you notice, your threshold actually decreases as we go down the periodic table. So the amount of energy needed to remove that electron is decreasing, which is why two gentlemen won a Nobel Prize for being able to make xenon and radon bond, because the amount of energy needed to remove that electron is much less than helium. Okay, now if it was just about adding an electron, we add a proton, we're adding onto the mass, protons, neutrons go into the nucleus, that becomes more mass if we add more electrons. If it was all just a simple shell theory, like what was produced by Bohr and Lewis, then this would all be linear. But we're noticing we have bumps. Why is this group below your transition metals? So we took another look at this. And we're going to notice some things here. Here we have 2 dots here, 2 dots here, 2 dots here. These are continuous throughout the whole thing. That's generally group 1 and group 2, okay? So there's your group 1 and your group 2. Your alkaline metals and your alkaline earth metals. And then we have, if you notice, we have this green group here. And what we notice when we look at them, right there, we get a decrease in energy when we add that 4th electron. We talked about this in our rules for Lewis dot, that we had to put in the electrons all with the same spin, and then we come back and pair them up again. Well, here's some reasoning for that. Okay, we're going to notice that we get a lower decrease energy when we add that 4th electron, which is our basis for believing that they come in there with all one spin, and then we double them up with the opposite spin. And then we have this red group. Now this red group, you know to be your transition metals. And so this leaves your F group, or inner transition. We're going to see very similar trends in all of them, but you notice how they're all grouped together, so that grouping is going to play a role in the electron configuration, which is going to support this idea of a quantum model. Okay, so here's what we're going to do. On our periodic table, we're going to take this time and we're going to add 2 lines. We went back, if we look back over here, we said that the element that's the hardest one to remove electrons from is helium. So I want you to draw 2 arrows on your periodic table showing that the ionization energy increases as we go to helium. Okay, that's all I've got for you right now. Have a great day.